So welcome to the Distinguished Lecture Series, Professor Sprinkle. Thank you for joining us today. Go ahead.
Thank you so much for the kind words and the fantastic introduction, Henry. When you were talking there about the I-Corps program, my mind was cast back to, I think probably it was the last time I was in Ann Arbor that I participated in the I-Corps in 2012 in that summer. It was the first summer that there was an I-Corps project node that was happening there. I have a lot of fond memories of tooling around Ann Arbor and eating great food and talking with people about innovations. It was really a fantastic time, and I really enjoyed it. Today, moving into some of the kinds of things that I'd like to talk with you a little bit about today is really something that harkens back to things that I was just learning at that time, which is what is the role that data can play. Not just in YouTube videos that can tell you whether there's a cat inside them or not, but in cyber-physical systems where there's dynamics that may have impact in how you would evaluate the success of what your system is doing, or how you would want to use that in a machine learning and artificial intelligence way. And as Henry mentioned a few moments ago in the introduction, I did spend a little bit of time at NSF talking about cyber-physical systems to lots of different folks. And cyber-physical systems itself really likes to think of the work that's happening there as driven by challenging needs in an application domain, such as transportation, such as manufacturing or civil engineering, the medical domain, energy, et cetera. Challenging problems that can't be solved right now that require innovation in fundamental core research. And so cyber-physical systems has always been driven by a challenging need that can't be solved, that brings together people who are application experts in that domain, as well as fundamental researchers or cyber-physical systems researchers who understand the complexities of multiple domains to which they drive forward to a common solution. And so when I talk in a few moments about this buzzword that you may have heard about before, convergence research. Convergence research really came out of a lot of folks realizing how useful this model could be. And in fact, when I was at National Science Foundation, I remember talking with some of my collaborators when we first started hearing the term convergence research being used. We kind of looked at each other and thought, this really describes what cyber-physical systems has been doing since the early 2010s, which was modeled in a way that a lot of DARPA research was done in the early 2000s, which was based on this final demonstration that you would do that really advanced the state of the art. And that experimental validation of your theory involved typically the capture of data. And the capture of data after they were validated were then disseminated throughout the community in order to demonstrate that the theory was working. And so it's always begun by having researchers in multiple domains, in this case, represented by these arrows, and then they come together. And as they come together, the domain expertise bleeds into the theory, the models begin to reflect the domain expertise. You validate the design of an experiment and you do some simulations to validate that experiment. And it culminates in this final experimental validation that provides you with that watershed moment in that particular discipline. So that's been a successful model now for several decades in how computing is interacting with the physical world. But where are things going in the future? The way things are going in the future, I would pose, is that those results that are being disseminated with data, we want to take those data now and have them be earlier in the process. We want to now have exploration of a role for how data can take a more primary role in developing your models and validating your design and even impacting the theory of what you'd like to do. Because as you'll see later at a societal scale, we can't depend just on theory, because the theory is a model that's only valid in some areas, and we need to understand when the model no longer becomes valid. I want to bootstrap the conversation by looking at two different kinds of experiments that have been part of the recent work that my team has done with other collaborators. One of them is, and I want you to think of them on these two different axes. So one of them is where we have a fairly small number of vehicles, but all of those vehicles have some kind of automation. That's, you can see here in the y-axis. And on the x-axis, we have a fairly large number of vehicles involved, but only a small percentage of those vehicles are autonomous or have any kind of automation in them. This really represents the two kinds of extremes that we're going to see over the next decade in this middle time, I like to call it. We're in this transition period between being mostly human which is where a very small number of the vehicles on the road will have autonomy, and always autonomous, where all the vehicles will be automated in some way, and where the coordination of all those automated vehicles could either be really great or could have not so great results. And we want to understand how to navigate this transition in a meaningful way, where we can be responsible stewards in society of the kinds of technology we're developing. So I'm going to start with experiment 1, which is this Jamaton stabilization ring road experiment. And many of you in the audience may have already seen results of this experiment before. I'm going to give probably the world's fastest talk about what the experiment did, because you could have entire talks and in fact days at workshops that are devoted just to explaining all the ins and outs of the experiment. Probably the chief result that you can see from here is that I'm the shortest jumper out of everybody on the team, that everybody else was either much more excited than I was or much more adept at timing what they were doing. This basically comes from an original idea about thinking of traffic waves as a phenomena that emerge despite the fact that you have no bottlenecks at all. And this really key experiment done by Yuki Sugiyama in 2008 has received a lot of public attention over the years. And it's really compelling in the sense that you see as the cars start turning around here, there's no stop signs, no merges, no traffic signals. Nobody entering or leaving the field of traffic. But what emerges are these waves in traffic, and you see one starting to form here right around the 3 o'clock range, and it propagates backwards throughout the field. So the wave itself moves backwards along the ring, and the vehicles just have or the vehicle drivers just have one job. The job is keep up with the car in front of you. And as you start to do that, as you start to try to stay at a certain distance, eventually some people brake a little much, some people accelerate a little much, and it results in these perturbations that begin to accumulate, and you result in these traffic waves. So what we wanted to explore was not just can we make traffic waves happen again, but can we do something about it? And that's what the entire project was based on, understanding how we can use a very small number of autonomous vehicles to positively disrupt traffic. So we emulated the Sugiyama setup in Tucson, Arizona in 2016. And for whatever reason, we decided to do it in the summer when it was something like 106 or 107 degrees Fahrenheit. And for whatever reason, again, all these delightful people decided to come out and do a bunch of driving over a period of 2 days. So we had 2 days of pretty hard driving with a bunch of drivers and a bunch of cars all rented from the University of Arizona's motor pool. And the result was that we got some pretty interesting outcomes just by trying to replicate that setup and injecting a small amount of control. So again, I could have a long talk on all the ins and outs here, but I want to focus just on the pieces that really relate to this idea of how data move along. So I'm going to play the video a couple of times throughout the talk, but I'm going to only talk through it one time, and that time is now. So right now, we can see this black arrow, which is pointing to the only gray car that's in the field. That's the Cognitive and Autonomous Test Vehicle, or the CAT vehicle. And you can see that it's in these traffic waves. At this time, we've transitioned from human control of the velocity to automated control of the velocity with our controller. And as you watch over time, these traffic waves that used to be so prevalent are now starting to dissipate. And there's a lot more information that's flowing along here than just how the traffic itself is starting to dissipate. We're able to measure the standard deviation of the velocity. We're able to measure the fuel consumption of the individual vehicles, how often they're braking, as well as how many vehicles are moving through a certain spot on the ring at any given time. And what's really neat about this is that we can see that we can continue to adjust what are the expectations for how fast this traffic can go. And we can see that there's a threshold past which it can't go, that even our automated controller can't stabilize the traffic. And so then we have to keep adjusting our expectations there. And finally, when we turn our controller off, and you can see the arrow is switched back to black here, that those traffic waves come back and we start to see the same kinds of high and low braking and velocity that we saw before. So again, there could be a lot of exploration of what's kind of going on here. I want to skip to talking about what are the data pieces that we got out of this experiment, because you can begin to see when you start to look at these data that there's pretty clearly at the beginning some times when we have traffic waves happening. When we turn on the autonomy, we see those traffic waves begin to attenuate and be dampened. And then over time, the traffic waves themselves really kind of go away until we try to go too fast again. So part of the overall control expertise that we're trying to do here is to figure out what's the best that we can expect from this particular traffic stream so that we can keep traffic moving and keep people safe. One of the nice outcomes, by the way, was that we discovered that there was something like a 40% decrease in fuel used between when the waves were happening and when we were in autonomous mode at about 7 to 7.5 meters per second. And that led to some follow-on work sponsored by the Department of Energy that I'll talk about just a little bit later. So the controller that we were using for this, again, came from exploration of how we could do this in a way that the cars would be driving as much like a human as possible. So I want to talk just briefly about what that controller was. It was a controller called the follower stopper, which was named because there was another controller called the obstacle stopper. This one is the follower stopper because it follows a car instead of just trying to avoid an obstacle. So essentially what we're doing is that depending on how fast we're going with respect to the car in front of us and how far away we are from that car, that we either project that we are acting safely or that we need to slow down and get out of the region that we're in. So these parabolas that scoot up over onto the left-hand side are telling the vehicle, hey, you can do whatever you want to do. You can just keep driving. You're in no danger of crashing into somebody. Or they're telling that vehicle, if the other person in front of you were to slow down, you could collide with them. And so we have a couple of different regions that affect whatever our desired velocity is to try to keep us out of this lower left-hand portion. Everything kind of on the southwest side of that darkest line represents that the person in front of you could cause a collision that you would be unable to avoid unless you exceeded your maximum braking that's allowed. And so as we move throughout the experiment here, we prefer to be up in this upper right-hand corner of the region of safety, because that's where we're able to control what's happening in the overall speed. And if we start to cross over any of those areas, that would result in potential disaster. So some of the cool things about this is that we were traveling at fairly low rates. We weren't moving that fast, up to about 8 meters per second, which is around 18 to 20 miles per hour. And with a fairly simple controller that doesn't get too far away from exactly how a human drives, we're able to dampen traffic waves, and the people who were following behind us had no idea whether we were in autonomous mode or not, which is really critical for the overall safety of what's happening. So we had a really great result there, again, with a small number of vehicles under our control and most of the vehicles being controlled by humans doing whatever they would do. The next experiment I want to talk about is doing high speed velocity control, where high speed isn't necessarily racetrack speeds, but it's more than 8 meters per second. We're talking in this case with drives that are in the neighborhood between 23 meters per second or so, 18 to 23 meters per second, which is much faster and therefore a much higher risk. And so we had to take a lot more precautions in what we were doing in this experiment to make sure that as we were driving around and doing a lot of these experiments, that all the people who were the humans in the cars were able to execute whatever they needed to do safely. So in order to mitigate this risk, we took a lot of time exploring how cars react to the cars in front of them when we're using their cruise controller. The overall approach of what this experiment was trying to measure was, can we line a bunch of vehicles up that have adaptive cruise control? And will traffic be better or will traffic be worse if we were to do that? The previous experiment was 1 out of every 20 cars being autonomous in terms of its velocity control. This is, for example, 8 out of 8 cars being autonomous in their velocity control. And we're using only the off-the-shelf controllers that are part of what ships with the vehicle when you buy it. And so we spent, again, a lot of time driving on these great roads in Tucson that have almost no turns and almost no dips. And so as we drive back and forth here, the car in front of us is slowing down and speeding up at prescribed intervals and prescribed distances in the velocity trajectory so that we can build response models based on system identification kind of techniques to build a controller response for how we think the vehicle might respond if we were to slow down. And then we can build a model that composes all of those vehicles in a line to try to see whether we can explore the overall string stability of the work. And just again, to reinforce why we chose Arizona to do this, I think this is also partially true in some areas of Michigan, that you have these nice long roads where you can see in a mile in every direction and know that nobody's coming. So that way you don't end up causing unsafe traffic scenarios in the work that you're doing. But because we kind of knew that we were going to be on the borderline of how vehicles were responding in a way that could be unsafe if people weren't trained about what was going on, we made sure that the tests we were doing with the hardware in the loop were ones where we could precisely control what the velocity response would be. And a lot of the work that we were doing was based on building state models for how the velocity controller should change states between different times and based on certain kinds of reactions to what was happening in the state space, so that we could precisely ensure that the vehicle's response wasn't going to result in unsafe behavior. So with that little bit of an introduction, again, I want to kind of skip a lot of things that went into this test that are really interesting, but take away from the overall time that we have with each other, and kind of just skip to the results, which any moment now should be coming. One more time with feeling. Yes, here we go. Again, this is a great example of some of these superb Arizona roads that have nobody on them. This is actually not a police car over to the right. It's just somebody's car that's parked there. So there goes the CAT vehicle in the front, and then we have several other vehicles behind that are just using their existing ACC controller to follow the car in front. So the CAT vehicle decreases its velocity by about 7 miles per hour total, just enough to turn the brake lights on, actually, which is why we chose that amount. The next vehicle brakes, it gets down to about 10 miles an hour, slowing down, then 12, then 15, then 18, then 20, until the last car, which was driven, by the way, by a qualified stunt driver, falls off so low that the cruise control in his vehicle actually switches off. And beeping sounds happen to tell you that a collision is imminent if you don't brake, et cetera. So it's really kind of a frightening thing. And what we saw was that if we put a bunch of cars that have existing cruise controllers on the road with each other right now, it does not make traffic better. It actually makes it worse. And that leads now to us thinking about, again, how do we navigate this time? But what I want to highlight for a few minutes is the test bed that we were using and how that test bed allowed us to come to some of these kinds of conclusions. On the one hand, we had this almost everybody automated kind of experiment that we did, where a lot of the things that we needed to have was model-based execution that could be safe at high speed, that we could verify the kinds of control inputs we were going to provide, and that allowed us to have really rapid in situ experimental changes. As an example of that, we would do an experiment, we'd come back and look at the data, and then in 20 minutes, we would decide how many cars we can put in the next string so we can run it again, and will that result in the potential for a collision, or will we still be safe? Certainly, it also involved in us figuring out kind of in the experiment, what should our intermediate velocity set points be so that we can trigger the ACC response. And so if we needed to do those kinds of things on a long time scale, it could have taken months to figure this out if we needed to go through code reviews, et cetera. What we were able to take advantage of was the code generation that's possible in model-based design so that we can make those decisions rapidly. In the experiment with the stop and go traffic dissipation, we really needed to have, again, that model-based code synthesis, the ability to look at system data in real time with the robot operating system, and to capture vehicle data for reasons that I'll explain later. And this all came through because of the CAT vehicle testbed, which is something that we've been building now for right around 8 years at the University of Arizona. And as we've moved through different phases of the testbed, I'm going to show you what some of the cool things we've been able to do and why this testbed is so critical to doing this kind of research, where it's not just building an autonomous car, but it's exploring the new theory and applications that we need to have for tomorrow's vehicles. The testbed itself is based on, like I said, kind of a long history of many people being involved, and many of the students that you see here are from the research experiences for undergraduates program that I'll talk about a little bit later. Many of them were undergraduates in the time that they worked with me and have since gone on to graduate school to do amazing things. And some of the students that you see at the bottom are the core contributors that have been involved in developing software that we've used summer in and summer out in order to make the system safe when we do the deployment in hardware. And if you want to find out more about the testbed or want to see kind of things that are happening with it, look us up on the CPS virtual organization, where you can find the most recent release and example tutorials to go through in order to see kind of what's going on. The testbed has two pieces. One of them is the simulation piece that allows you to do software in the loop testing. This gives you a full-size looking Ford Escape, which is the kind of vehicle that it is. And that full-size vehicle, we can drive around. We get realistic information from the sensors on board the vehicle. and we get realistic masses and dynamics for how the vehicle itself behaves. Importantly, we are consuming data that comes off of the car in the same structure and at the same rate that we get those data when we're using the car physically as a test bed. So for example, we were able to use some of those kinds of features of the software in the loop test bed to validate that we weren't going to crash into stationary objects by creating an environment filled with stationary objects that we tried to drive through. So what you're seeing in the bottom right-hand corner is me trying to drive through a house. I put a house in the path of the trajectory that I was trying to follow. And I'm not trying to navigate around the house in this case. I'm trying to actually drive over it. And so I've got a component that's inserted in between my desires, which is my desired trajectory, and the vehicle's desire to not crash into houses or anything else that it can see with its sensor. And so one of the cool things you can do in simulation is that you can just pick up stuff and move it. So I can keep picking up the car. It keeps trying to drive through the same area. So that gives us some ideas that it's robust position, that it's not just something that we're lucky. And something that you can't do in the real world, you can't just move the obstacles out of your way like you would move a house. But in simulation, you can. And then we can see that the vehicle is able to take off and drive around. So by building up this kind of sort of good feelings about how your vehicle is doing in software in the loop, you can get rid of a lot of the logical errors that you might have introduced in handwritten software by checking to see how things are going with software that you're generating from Simulink-based controllers, because you can test them in Simulink and then move them to the software in the loop test bed. Once things are working in the software test bed, we can move them to the physical test bed. In the bottom left-hand corner here, you can see results of an experiment from some of our summer students who were testing that controller that's designed to not drive over physical obstacles out in the middle of this parking lot that's filled with light poles. So if you want to make the dean of your college really nervous, you can say, hey, can you give us a parking lot with a bunch of obstacles in it that if we run into them will cause a lot of damage to university property, because we would like to test our controllers. The dean gets really nervous in the beginning until you can show them that it's working in software to give them the confidence that they're willing to let you go out there. And of course, it's on me if we actually hit one of them, it has to come out of my paycheck. But that's part of the overall approach that we're using here to build up that kind of confidence and use the tools that are available to the state of the art in order to validate that the work seems to be working. The way that we're able to do this is that we're able to depend on a lot of software at different layers of the interfaces so that we can get the kinds of performance that we need to do in order to do real cyber-physical systems kind of research that we can scale to a societal level. And we're able to do that because we have access to the low-level actuators and sensors of the car. We have access through ROS to be able to send essentially computer commands to the OpenJAWS framework that runs on the car. And then ROS itself allows us to consume data from sensors. Somebody else is writing all of that code and we're able to just leverage it to produce these topics that allow us to get state information as well as control level information about what's going on. What we see as we develop and build this as a tool that we want other people to use instead of just the people in our lab is that we'd like to have an engineering or scientific workflow that takes you from your idea to the implementation and allows me as the overall gatekeeper to how people should be using the test bed to ensure that we're doing it in a way that I know to be safe by the evidence produced by the students or the other faculty who are using the test bed. So we begin by having some traditional kinds of simulation like you do in MATLAB and Simulink. We replace the synthetic data sources that might come from the sources blocks within Simulink with data that are coming directly from something that's recorded on the car or something that's recorded from the simulation environment. We validate those kinds of behaviors within Simulink. We generate code using MATLAB Simulink's code generation feasibility tools to generate ROS level software that we can then run in our software in the loop simulation and then directly deploy in the hardware in the loop to either simulate with, again, canned data or to use the physical platform and then do work there. So by taking advantage of this kinds of work, we can stage different requirements of the process and take a more agile approach where every stage in the process has a different requirements level that you're meeting. And then over time, you build confidence of how your system is behaving. And it stages actually really well that over a 10-week period, for example, in the summer, that our undergraduate students can go from knowing almost nothing about autonomous vehicles to be able to show a final demo with a car moving around in a parking lot with nobody inside, which is really nice. So I'd love to say that it's really that easy, that that's all you really need to do. in order to have a test bed like this that can do really crazy research on short time scales, that all you need are those software layers, and you can use those software layers at different phases. But unfortunately, it's not actually that easy. If you want to be able to do some of this kind of societal scale research with cyber-physical systems, you need to get an idea of what kinds of challenges you might run into when you make those deployments. So for example, two things that I want to talk about fairly briefly are the kinds of delays that you see in sensing and filtering when you want to deploy a system like this, as well as delays in the actuation and dynamics that you have to take into account if you actually want to do time varying kinds of control with a system like this. I'll talk about it first in terms of the follower stopper that you saw earlier. I think you probably remember this slide where what I'm showing over on the right is the distance between you and the car in front of you, which seems like it's something that, yep, if I had that distance information, I could design a controller like this and we could make it happen. And many of you in the control area might actually have looked at this controller and thought, that's a really easy controller. There's kind of not much to that. I'm not really sure what the threshold had to be to have a more sophisticated controller that might be able to do more sophisticated things. And one of the reasons we ended up using the controller that we did was trying to mitigate the challenges that we had in using real-time sensing so that we can make real-time decisions based on the data that we had. So for example, if we just sat behind a car in the parking lot and both we and the car ahead of us moved at the same speed, we would sometimes end up with these vastly different estimates of kind of what's happening. And so actually the top two charts show you what happens if we just sit in front of a wall and run the laser sensor and estimate the distance to the target. Sometimes we get these really large distance estimates that if we interpolate them and divide by delta t, we end up with an estimate of say 4 meters per second, when in fact the obstacle is not moving at all. And so we have to be able to overcome these kinds of things by adding filtering to the system. But when you add filtering to the system, what you end up with is delay. So in this example, I'm actually playing the same data set that gave us the estimate of the phase space of relative distance and relative velocity of the car ahead. But on the right-hand side, you're getting the raw data from the laser sensor. And so you have to make this trade-off between how many steps do you want to sample so that you can get an understanding for how far away you actually were and what your relative velocity actually is, versus over on the right-hand side, if you want to act on the most recent data, you're going to be stopping a lot more than you should be because you're going to be getting these outliers that make it look like that you really need to stop when you actually don't. And where this really matters is that if you wanted to use some of the more sophisticated control algorithms, and what I'm showing in the simulation at the top here is an original controller that we designed that seemed to show a lot of promise, because when the AV was active, we were able to see a tremendous impact in the positive behavior of the overall stream. But when we tried to execute the controller outputs that we got from that controller, we found that we weren't able to execute them, both because of problems in the sensing delay, as well as problems in actuation, which I'm going to show you in a few minutes. So that's the other half. This delays in actuation and dynamics limit what it is that we're able to do. And we need to overcome that also through software interventions. For example, if somebody had given us this trajectory, which is a velocity trajectory that we'd like to follow, keep in mind, again, this is not a drive that we're trying to navigate this as an XY position. This is a time varying velocity that we need to match because we need to be going at a certain speed at a certain space in order to dampen traffic waves. So we tried at first to just take this output from simulation and execute it on the car using hardware in the loop execution to see how it would work. And the answer is it did not work at all. Using the canned controller that came with the vehicle that should be helping us to match the velocity, we found that instead of matching this velocity curve, we actually ended up stopping. And it's kind of a worst case scenario when you're trying to keep traffic from stopping, and the controller that you're using to keep traffic from stopping is actually making your car stop. And so if we tried to execute this controller, without a doubt, we would have made things worse and not better. So we took advantage of some of these software interface layers and were able to build some new low-level controllers that were executing at this ROS to JOS and OpenJOS layer instead of just the ROS layer, so that we could inject new controllers that had a faster response time in accordance with the dynamics that we had, so that we could follow time varying trajectories a little better. And again, I think actually Ram Vasudevan, who might be on the call, he and I had a tutorial session at CDC last year, so you can find a lot of the code on this based on that CDC tutorial session that takes you through this. Essentially, we built some car-like dynamics based on system ID. Once we had the dynamics from there, we designed and prototyped some PID controllers based on some off-the-shelf techniques. We tested it with hardware in the loop, and then we found that we were able to follow this representative curve much better. So over on the left is the original approach, over on the right is the updated approach. And even though there's still a few warts here, those warts actually fed back to the design of the simulation tools to say, you all are braking much faster than we can brake. The simulation tool has a much wider state space available to the car than we can execute on the car. And that's important information when you're developing your simulations as well as your safety tools to understand what are the physical limitations that are out there. So we had to go back to the drawing board and develop some new controllers at that point so that we didn't find ourselves thinking that we were safe when in fact we were not safe. And I think that's overall one of the messages that I'd really like to get across, is that to do this kind of societal scale work, the research test beds really need to enable you to go beyond simulation when it comes to these kinds of challenges. Or what you'll find out is that you'll show up somewhere to show a simulation to somebody and they'll say, that looks great, but we're not sure that those simulations are going to translate to practice or not. So reflecting on this from the Arizona Ring Road experiment, again, thinking about that role of data and how data is going to play significant impact on societal scale work. If we think about all the different pieces that went into the work that we did for culminating in this final autonomous vehicle experiment, it began with fundamental research on wave theory. That culminated with transportation research on this green-based simulation that you can see here that seemed like it was going to go well. From the CyberPhysical Systems side, we tried to simulate that and realized that the simulation engines that we had just would not work. And that meant that we needed to skip a lot of the simulation that we would have done and instead do it directly on the vehicle, which required us to come up with controllers that were safe, that we knew we could deploy in real time. And fortunately for us, all three of these led to this experiment that resulted in lots of really cool data that popped out of it and really serves as that model of convergence research. But I want to talk just briefly about the challenges that we saw in data capture, again, just 5 short years ago, and kind of what was going on. What I'm showing you here is my student Armani Halsey, who's now a PhD student at MIT, but she was an undergraduate student at the time serving in the REU program. She is actually installing an onboard diagnostics or OBD2 link into the car, and we had to configure these things to work with an Amazon Fire tablet that was synchronized to GPS time to offload USB data for all 20 of the cars that we had in the experiment. We had cameras in the sky that were recording what was going on. And we also had the CAT vehicle, which had the onboard diagnostics tool installed inside of it, as well as its own data gathering that was there, including the forward-looking LiDAR sensor, as well as all the wheel encoders and internal velocity that we knew that we had. We were also getting data from these 360-degree cameras, which gave us the final estimates of all the velocity trajectories, position velocity and acceleration. And so we ended up with something like 20 of these kinds of videos that you see here, where the real-time version is at the top and then the sped-up version is at the bottom. A tremendous amount of effort in computer vision went into doing background subtraction and vehicle position estimation of all those little cars that you see on the screen, to estimate where they were and give us data updates that we could differentiate in order to find the velocity and acceleration there. So the data capture that we did was laborious. This is probably the kindest way to describe it. And we had to then validate the data that we got from the camera sensors and the OBD sensors based on ground truth information that we had from the CAT vehicle. And so what we ended up having to do was spend essentially weeks, maybe even months, making sure that the data that we were using to validate our work were valid, and that those we weren't having something that we were going to be using later to design a controller based on data that were potentially flawed. So that really calls into question, again, how we can make sure that the data that we're using here can scale and how people can really trust what's happening there. So those 3 challenge problems that we had, if we can solve the first 2 of them, what we can end up doing is then accelerating that role of data in discovery. And that's where we run into more challenges, because even if we can solve those 2 problems, we're going to have an issue, which is that a CAT vehicle or something like a CAT vehicle is not affordable to do at scale. We can have a couple of these, but we can't have some that exist in all areas of this pipeline so that we can produce hundreds of cars that might be driving all at once, that are all coordinating what their velocity is to make traffic better. And that's where we start talking about what could I do if, say, I wanted to have 100 cars that I'm controlling all at once, which is exactly what we're working on in a Department of Energy project that was funded right around a year ago with Alex Bayan from UC Berkeley as the principal investigator. This involves collaborators, Benedetto Piccoli, Vinny Zeibold, and Dan Work as well, if you know any of those folks. Really what we're interested in doing at the end of the day is actuating up to 100 cars at one time, where up to 2,000 cars are going to be affected by the intelligent design of our system. And in order to do that, we can't just have 100 CAT vehicles, but we could possibly find 100 off-the-shelf cars that have many of those same capabilities if we can bring that data and actuation costs way down. So what we're taking advantage of is what many of you may know is that cars today have a lot of these data capabilities already built in because they're building safety features for consumers. And so if you know information about how far away the car is from you for advanced adaptive cruise control or for pedestrian detection or lane keeping, all you need to do is figure out how you can tap into those connected components and attach your own database so that you can get the features off the car and then make decisions based on what's happening there. Companies are entering this space right now. So if you're familiar with Comma AI, you can buy something from them called the Black Panda. Once upon a time, they had the Gray Panda. With this and a car harness, altogether total, it's about $500. You can download a lot of cool data and do a lot of cool things with your car, but you can't get it at data rates that are suitable for research. So what we're seeing here is that some of the data that we're getting actually end up representing lost packets, and therefore you can't differentiate the data reliably. You might be missing important data, and that reduces your ability to use these data in machine learning kinds of contexts. So what we need is to take some of the data acquisition that we're doing and make it research quality, which is what many of the folks in my lab are now working for. And that's going to give us opportunities to automatically add structure and to bring more data gathering at the lowest end of that triangular feature where we're doing the convergence research to enable you to use analysis tools for data science faster. So to take you just kind of briefly through some of the kinds of cool results that we're able to do with this, I want to talk a little bit on the acquisition side for capture and control with this software package called libpanda, as well as on the analysis and discovery side with an analysis tool called Stream. You can find some more information on our GitHub page about this, but essentially we can use a Raspberry Pi with a couple of off-the-shelf pieces here and some customized software that we have in order to automatically gather data from the car. So as soon as the car turns on, we use the GPS to set the time based on what the current time is. We record while the car is driving, and then as soon as the car turns off, we actually have some onboard power. Hopefully you can see this on the screen here, which allows the Raspberry Pi to stay on just a few minutes longer and upload its data if it's connected to a Wi-Fi network to a shared cyber infrastructure called Cyberse. Once you get those data, you can start to explore a little bit about what's going on there. So for example, in this particular vehicle data file, we can look at the speed information, which has message ID 180. With some CAN debugging tools that are built into the Stream software, you can start to now take away the pieces that you don't need from the data stream in order to find the actual speed that you'd like. But you have to be careful about the issue of time, as I alluded to before. So if you look in that left-hand column, all of these data streams have exactly the same time. So we've done a significant amount of work in trying to make sure that as we're gathering data, we can validate that the data are coming in at rates that are suitable for research. And that was really the genius of the libpanda design, that we were able to translate a bunch of stuff that was written in Python, which is really good for data analysis. And we were able to accelerate that through C++ so that we can have confidence that the data rates that we're getting are ones that we can use for control. So in the last year or so, we've gathered something around 20,000 kilometers worth of driving data from a bunch of different cars that are part of our research study. And we're going to be gathering more soon. The kinds of data that you get from these drives include the ability to look at the velocity as a time series, to correlate that with the acceleration data that you're getting, or to maybe even look at how a particular driver happens to drive when they turn into a parking lot or as they're moving along on the highway, to compare their steering angle to their speed, for example. We have some really cool dash cams that are attached to the cars that allow us to correlate what's happening on radar with your speed, with what's happening in the environment. We can look in data at aggregate to get information about how a person happens to accelerate or decelerate. And if we find outlier data in there somewhere, we can say, hey, I wonder why I had this massive deceleration here. It allows us to zoom in on those data, maybe compare it to the radar data and see that there was a point here, I don't know if you can see my mouse, where somebody pulled in front of us and made it look like that traffic was beginning to accelerate. And then they got out of our lane and then we had to slow down PEQ. So exploring these data is part of the stream infrastructure that allows us to extract data from those CAN files, to analyze things like the speed of the car, to get information about how far away the lead vehicle is from you based on radar data, and to look at information like what's the radar look like all over time. So here's an example of all the radar traces we got from this particular track over an entire drive, so that you can see exactly what your radar range and angles are. We can even overlay this on dash cam footage, and I'm just going to really quickly show you. I have to skip ahead in the video here to be able to see that. In the bottom right-hand corner, you see the dash cam from this car. We can see that there's a car in one lane to the left of us, as well as one car in front of us. And those correspond directly to these kinds of blobs that you see popping up on the RViz piece here, which gives us an idea that we're able to actually see in ROS in real time exactly what's happening to the car. We can even correlate the data, for example, only when cruise control is off. So we're getting state data about the car that allows us to break it down into regions where I know that I'm getting specific data about how this driver is driving when they're following another driver and somebody's in their blind spots. We can have a lot of these things as sort of database queries now. And once you're able to get data at that scale, you're able to start looking at an actual driver's behavior and get naturalistic driving at scale with $800 a vehicle instead of, say, $8,000 a vehicle of equipment that you have to add. And that's going to bring us a lot of these kinds of discoveries in these human-in-the-loop systems, which is a really exciting new frontier. How can we correlate data from the sky that might be coming from cameras with the instantaneous data of all the vehicles, or a subset of the vehicles that might be moving through the flow? I'm going to wrap up by talking not just about the Convergence research side, but how can we play this into Convergence education? How can we take the outcomes of these data and have them feed forward into the kinds of work that students are doing in classes? So I have two examples here that you can learn more about later, which is how I was able to use some of the work in the original CAT vehicle experiments for driving around in a circle by giving those LiDAR data to students and having the students in sophomore level C programming classes interpret those data, design their own filters, and then compare the response of the vehicle in simulation with the same kind of responses that we saw there. So the data are playing a huge role in teaching students about how they can take advantage of data for what they want to do next. What else can models do for you? They can broaden the user base. And so this is an opportunity for me to show off a lot of the work that our amazing undergraduate students have done who've come for the summer program for the CAT vehicle. One of my favorite videos actually features now a University of Michigan graduate student. So here's Adam and Liz following a car in front of them, just using the camera from the back of Adam's phone. So he's able to estimate how far away the car is, and they're directly controlling the velocity of the car based on commands that the phone is sending to a laptop, which is really kind of great. We also had some fantastic examples of students who took existing theoretical research and translated that into hardware-in-the-loop experiments in just about 6 weeks, which was really amazing. If you want to learn more about that, you can find out more on our YouTube page. What JMS CSL group is a great place to find the videos of all the students who come through our program. And I'm really, really proud of all the work that those students have done over time. Over the last 8 years, these students have come miles and miles with the work that they've done. And even last summer, they were able to, despite the pandemic, produce 4 groups worth of really amazing research that I'd love for you to know more about in the time that we have left. The thing that I'll close with is thanks so much for the support from the National Science Foundation, not just because of what they've been able to do to support the research, but also to support the research participants. The people who've come through the CAT vehicle REU site have much more confidence in the work that they do. They understand more about research and cognitive radio, machine learning, and autonomous vehicles. And one of the truly amazing outcomes is that we don't require that they go to grad school, but we really strongly encourage that they apply. And out of all the students that have applied in the last 8 years, that have graduated, something like 87% of those students have gone on to receive a fellowship. They may not have taken the fellowship and they decided to still move to Silicon Valley, but they gave themselves options that they wouldn't have had otherwise. And that's kind of how I'd like to close it up. Think about what you can do for broadening participation in computing, broadening participation in engineering by thinking about what's a target audience that you believe that you could empower in the future who currently doesn't have opportunities now. And think about ways that you can make a difference by empowering them, either by more training that you would do or more focused opportunities that you're going to give to them. So I think I'll leave it for that now, and we have just maybe a few minutes left for questions. Henry, I'll turn it back to you.
That's great. That's a great talk. Excellent and very inspiring. I really learned quite a bit from you from your talk. I also fully agree with you that translating some of these basic fundamental research into a society impactful research, it's not easy. And translating simulation models into implementation is not easy as well. As we do some of the work, we instrumenting with vehicles and we translate those into the field practice, and we get the same feeling from you as well. But those are very, very important, and it's not only important for research, but also, as you point out, important for education as well. And this is amazing how much work you have done in the last few years. I do have a little bit technical question. I want to ask you. Maybe I just take the because I'm the moderator. So you talk about when you put the autonomous vehicle sort of in a circle, and then you can somehow dampen because the reaction from the autonomous vehicle, you can dampen the traffic flow congestions over there. What about if you put it into like insert in urban arterials, not in a freeway setting? And then when in that setting, you will also have some sort of lane changes, and some people, maybe get into your fleet of vehicles. Do you have any sense in terms of how these will impact this? And then the autonomous vehicle will be able to sort of like a flow regulator, in the urban arterial sense.
Yeah, I'm not working in that area, but I know a lot of folks who are thinking about, for example, platoon forming in red light timing so that you don't end up slowing down as much. I think the controllers are a little different in that case, but the opportunities are still there. And it's been exciting to see how some of the folks who are doing this, and I saw some simulations from some people a few weeks ago on a separate project funded by Department of Transportation, FHWA, that they were realizing that if they had too much delay in the communication between vehicles, that it actually made things worse. And that's exactly the kind of discovery that we'd like to find out in simulation before we put it out there in the field.
Okay, and I also get a few questions from the audience, so I'm going to read these questions to you. The first question is, does much of the stuff off the shelf support technology create cybersecurity challenges for AV in the future?
Yeah, many of the cybersecurity challenges are not to be ignored. Even though it's not my area, it's something that I would really love to work more with folks on, because I think there's opportunities to use correlating streams of data to confirm that you're not having injections from a false party or from a third party. And so I don't want to just listen to anybody's command for velocity or acceleration. I want to know that they're the person who I think they are, and where they are, and the things that they're seeing, for example, in their sensors might be able to correlate with what I see, so that I have high confidence that it actually is the car next to me, for example, and that it's not coming from a satellite somewhere. That's a fairly, really excellent question.